you need, right? So it's a search functionality. Once you have the find your product and it's to your liking, you start making payments and ordering that item, right? So payment functionality, and of course there needs to be a user management again here, because you log in into your shopping app to your account, to see what you ordered, user specific things. And there is a cart. We like some products, we move it into cart. So I'm not listing every functionality there is, some of the main functionalities or core functionalities of any shopping app. Let's take these and try to understand microservices, what microservices does. Okay, so this is a typical shopping app which we have an idea of. So yeah, uh, earlier times when you wanted to deploy this shopping app, you used to deploy everything as a single application, right? That application used to have these features inside it. So it was called as a monolithic architecture. So you would store all the code for uh, the shopping app in one Git repo, and you'll have different methods, maybe catalog, main catalog, and then main search. So within a single application code, there might be different classes like catalog class, search class, payment class. So that's how you would code normally in a monolithic architecture. So it's a software design approach where an application is built as a single indivisible unit with all its components like catalog, search, and payment tightly integrated. So tight coupling is there. This means the user interface, business logic, data access layers are all part of the same code base and are deployed as a single application. While uh, it is easy to get started with monolithic architecture. So whenever someone is starts writing a code for a small scale application, then monolithic architecture is what they will choose. Okay, but as the application grows and company grows, it becomes hard to maintain. Okay, so there are some advantages and disadvantages to monolithic architecture. So we'll just see them. um, as I said, it's suitable for smaller scale applications because it's easy to code and it's easy to deploy. Why is it easy to code? You don't have to bother about dividing your application. You just keep on coding your ideas as a single unit. Okay, if it is a small scale application, then you can make use of its performance. And since you are not spending any time dividing the application, it increases your efficiency. Since you have only one unit to manage and not several units, there is a reduced operational overhead, and it's suitable for small scale. What are the disadvantages? So let's say your application grew to some your application size itself is let's say 1.5 GB or something like that, and there is a heavy incoming traffic and you want to run multiple instances of your application, like replicas, right, to handle all the traffic load. Then that is called scaling, right? So scaling this 1.5 GB application as a whole becomes a challenge. Okay, and all the if you say if someone wants, let's say there is a bug in this payment feature or payment class, then let's say you fix it, but when you deploy, you when you deploy this fix to production, you have to deploy entire application again. You don't have any way of isolating that payment and fixing only the bug, that service, because it's all tightly coupled. If you want to redeploy any feature of the application, you have to deploy the entire application. Okay, so it's tightly coupled and it's difficult to deploy. uh, and all the features which you have, you have to code it using, you have to select only one language for your application, because it's a unit as a whole. You can't have payment service in Python and search service in Java. Okay, so entire thing has to be written in one coding language. So there is limited technology choices. Slow development speed. Why is it mentioned? Advantage it's speed, and in disadvantage it's mentioned as low speed. It's in terms of smaller scale and larger scale. If the application is small, then it's faster, but if as the application grows, it becomes slow. Okay, and it's a single point of failure. Let's say if some developer pushes in code, like in a faulty code into a catalog function, then all the other services are also impacted, like search functionality, payment. Your application is deployed as a whole, its life cycle is tightly coupled, so any faulty code will bring down the entire application, not just the catalog service. Okay, so let's look at microservices architecture. So just a second. So as of now, there are only like monolithic and microservices architectures. Uh, in microservices, why even this idea came? What problems does it aim to solve? Okay, let's look at that. So this is also a design approach where an application is built as a collection of small and independent, loosely coupled services. You are dividing the features that your application has, and you are deploying them individually. So catalog is deployed as a separate application, search is deployed as a separate application, and everything else. So now you can almost see various advantages by doing this, right? You can um, you can have catalog service written in Java service, you can Java language, you can have payment written in Python, and UI code can be written using some Angular JS or whatever UI front end frameworks there are. Okay, so you can leverage multiple technologies or benefits each technology provides for your services, right? These services which are deployed individually, they communicate using API protocols. It's a lightweight protocol. API, you might have heard of it, application programming interface. So each service communicates with the other service using API protocols, and there is no tight coupling. Um, and that's why, see, let's say if you have a faulty code in catalog, the same example previously, only the catalog service is down, so your application is still up and running, your payment service is up, so cart is up. If someone is in the middle of payment, since your application is not going down just because of catalog, they can use and you know complete their transactions and all. So you are minimizing the area of damage by going for microservices architecture. So let's see. Okay, yeah, the code is also different. Okay, we'll look at how microservices code is managed. uh, you can have, as I said, catalog can be written in React, and you can hire React developers which who are experts in that. So you can have different people with different expertise work on a single application. So search service can be in Java, payment can be in Python, card can be in TypeScript, user management can be in C++. So all the services communicate with each other using API protocols. So what are the advantages and disadvantages? As I said, scalable. So when you have, when you put a sale like Amazon sale or something, uh, obviously there will be heavy traffic. Lots of people will be browsing your shopping app. So you want there to be lot of catalog services available to handle all the traffic. So you now in this microservices architecture, you don't scale entire application. You are just scaling catalog part of it. This catalog, there can be 10 replicas, let's say, and user management, there can be only 2 replicas maybe, depending on the load, right? That's why scalability becomes easier. You can only scale the service which you need to. Fault isolation, as I said, if there is a faulty code in one service, it does not impact other services. Your application as a whole is still running. Diversity, in the sense, I mean, you can have multiple people, multiple technologies, you can leverage benefits of each of it, and flexibility. Yeah, but since you are deploying these services as individual units, you need to handle the networking part of it. right? So there is clearly it seeing this diagram only, it's already a bit complex. We have taken only a few features of the application, but you can already see lot of confusion going on here, right? It's a operational overhead because you have lot to think about. Now different people need to interact and see how this application needs to function. Okay, communication is there between the services, between the teams as well. Lot of operational overhead is added, increased costs, because you are hiring different people, leveraging the benefits of different technologies. Obviously you have increased people to pay. Okay, each service needs to run in a different environment because they are using different technologies. Okay, so there will be increased cost for that, and you need to keep the data consistent across the services, like across the teams. Okay, so as I said, microservices, you can have you split the application into different units and code them separately using different technologies. So how is the code stored? Like, do you store catalog in its own Git repo, search in its own Git repo, or you will create a repo for the entire application, but have different folders for catalog, search, payment card, and user management. So, which is basically monorepo. So in monorepo, you create a single repo for your application, like shopping cart, and then you have different folders for each feature you are adding into the application. Okay, so in polyrepo, you have multiple like different repos for your different applications, and each repo is not dependent on another. So each again has their own benefits and disadvantages as well. So let's take a look at that. When you say simplified code sharing, that means the code can be shared easily, and libraries, there will be common libraries, right? So in a enterprise level the code application, there will be base modules that are written, and they are used in multiple features of your application, like using the import statements. Like in code, you do import pyml, import my module, something like that. So you don't write the modules again and again. So when your code is stored in a single folder, you can have the common libraries in a single place, and multiple features or multiple classes can import these same modules and reuse the code, right? There is improved collaboration and consistency across teams working on different parts of the system, and streamlined tooling can lead to be it's more efficient tooling and workflows as everything is in one place. I mean, monorepo, you can find it a bit weird, but large companies like Google, Facebook, Twitter still use monorepos. It all depends on how what your application is and how your teams are functioning, right? So each has its own advantages and disadvantages. It's not like this is 100% perfect. Uh, Depending on your situation, you need to select which to go for. So the disadvantages of monorepo is complexity. Again, we are when we maintain the whole code as a single unit, we are still keeping some of the disadvantages from the monolithic architecture, right? So in polyrepo, the advantages are project isolation. There is no tight coupling at all. Each service is individual, and there is no dependency. But the common libraries which are there, it needs to be maintained in every repo continuously. So let's say if you want to make any changes to the common libraries, you have to go to every folder and change the libraries, and make sure that you have changed these libraries for every service, or else again if the service will break. So it's dependency management is hard, collaboration is a bit hard, smaller code bases, because since you are dividing the entire feature into a single thing, if the application as a whole is 1.5 GB, when you split these services, each might be a 200 MB or something, and it's easier to deploy and faster to deploy, right? Now let's see what containerization is. Uh, since we are splitting this application into multiple features, each service needs to run separately, right? But we can't have entire physical servers only to run a small feature of an application, right? So in a single server, we need to run multiple features of an application. So how can we achieve that? That's why people came up with some technology called containerization. Containerization was already there in Linux. Okay, it can be achieved using these C groups and namespaces. There are Linux concepts. With those concepts, containerization can be achieved, but Docker took it to the next level and made it a lot more practical and popular. Okay, so when a developer writes code for an application, why this containerization is needed? First of all, let's see at a practical example. Okay, one developer is there, he will write code for an application. Okay, when that is tested in his system, it will work. But when he uh, he will do unit test, right? His own laptop, developer will do unit test, and he thinks, okay, my application is working, and he will send that, I mean, commit that into the Git repo, and tester next, what he does, tester need to test various scenarios again. So when tester runs the application, it doesn't work. uh, but developer says it works on my system. I don't know why it's not working for you. But both are using Python only to run the application. But why is there such difference? So developer might have 3.8 version of Python, but tester might be using 2.3 version of Python. So developer system is Linux, but the tester system is MacBook, let's say. Okay, so there might be different configurations, several things that might cause this difference, uh, because developer developed using these configurations or this environment, and there is a different environment that tester is testing the application, it may not work. This might be one of the major causes why there is a difference. Okay, so what containerization does is it will write everything, right? It will take the what it does, it will take the versions of the libraries, the OS on which the application needs to run, the configurations, dependencies, everything it will take, and it will put into a box. So when tester wants to test it, he will just takes this box and he will run it again. So it when you run it from this box, you are basically having all these. It's not dependent on what operating system or what configurations the tester's laptop or tester's system is using. I mean, tester is using, right? Uh, because we are mentioning everything that the application needs into the container, we are packaging everything into the container. Tester will just use the container's resources only instead of his own system's resources. With containerization, you pack an application and its dependencies like libraries, binaries, config files into a single isolated unit called container. Yeah, as I said, it uses C groups and namespaces of Linux to achieve this containerization. So why do we need containers, right? So they are lightweight. As we saw before, an application as a whole might be 1.5 GB, but the container is a part of the application, so it might be 200 MB, right? It's lightweight. Since it's lightweight, we will look at something called images going forward. So we can have images which are portable. You can just share it like a in the mail or from the repo. Like, it's lightweight and it can be easily shared. So there is consistency there. This is a strong point because the previous example was regarding consistency only. Uh, you are packaging not just the application, your entire configuration that the application needs. That's why you will not have problems like it works on my system, I don't know why it doesn't work in your system, because you are sending the entire OS configurations, everything along with the application. So the resources used are efficient, scalable, and faster deployment. These are all again from microservices only. Scalable, I said, only a single part of the application can be scaled according to our needs. Since it's lightweight, when you send it to some server, uh, the transfer is really fast because you are not sending 1.5 GB application, you are just sending 200 MB image. It results in faster deployment. So the popular tools which achieve containerization or which are used to work with containers are Docker, Podman, LXC, LXD, and Builda. Um, Frankly speaking, Docker is the only one which you need to learn. So Podman, if you are interested, you can go for it. So let's understand what is the difference between container and a virtual machine. So does anybody know what a virtual machine is? If I mean, did anyone work with a virtual machine before? Back in my time in college, in my college days and all, we used to have a Oracle virtual box. Okay, it used to be a software that we used to run on Windows operating system, and we used to select how much CPU, how much memory, hardware resources that we need to allocate for that VM. And when we clicked on run, it used to take like 5-10 minutes, and it used to spin up a virtual VM for us, Linux VM inside a running on the Windows. So, does anybody has any familiarity with that? Okay, so it's a 90s thing now. Okay, fine. So, let's say any system will have a hardware, right? It will have a CPU uh, and other hardware components, right? So, any operating system will have this hardware, and the host OS kernel will be there that will make use of this hardware, and it will run the OS. And on this, there will be application layer uh, where we run our applications like Chrome, any games, any applications we have, right? So in case of virtual machines, everything is virtualized. So from the hardware to the application layer, everything is virtualized by a layer. There will be a layer called hypervisor, and it will take care of all this virtualization. Just remember that virtual machines will virtualize every layer from hardware to application layer. But containers, what it does, it will only virtualize application layers. This difference is very important because containers, they don't, since they don't virtualize the OS kernel, if you are running multiple containers on a single system, all that containers will be sharing the same OS kernel, right? If one container is hacked or compromised, then they can make use of the OS kernel to hack all the containers. That's why containers are less secure than virtual machines. Virtual machines, they virtualize everything. So even if the virtual machine is hacked, it's only the virtualized part that is hacked. They don't have any way of getting into the underlying operating system on which this virtualization is running. So that's why this is more secure than containers. VMs offer a strong isolation between the operating system on which a virtual system is running, uh, and their resource usage is also high. Okay, they use more resources like CPU, storage, memory, because each VM has its own OS, right? Because on a Windows you are running in Linux, right? So you are loading entire Linux operating system every time you spin up a virtual machine, leading to higher overhead and slower startup times. So in if you have heard about these cloud providers like AWS or GCP, they'll have these EC2 instances, right? They are basically virtual machines. They are not containers. So this is not outdated technology. It's still being used. That's what I wanted to say, right? The use cases of virtual machines, they are suitable for applications which require strong isolation, dedicated resources, and scenarios where full OS control is needed. Okay, I think these are all the points which I just mentioned. And containers, as I said, they virtualize only this layer, allowing multiple containers to share the same host OS kernel, making them more lightweight. Since you are, every time you spin up a container, you are not loading the OS. You are just running application layer. You are just virtualizing one layer out of the three. So it's faster and take very less time to come up. So containers also provide some degree of isolation to till the application layer, but not as much as virtual machines. So this could be a potential security concern. Uh, Resources are efficiently used in containers rather than virtual machines. Okay, so any questions so far till this point? Okay. Now, as I said, there are multiple technologies which use containerization, and Docker is the popular one out of that. We'll be looking at that today only. So when you work with Docker and when you start working with Docker, or when you say you know Docker, you need to have knowledge on these particular terminologies. Without understanding these terms, you can't understand what Docker is doing, right? So let's look at these first. So there is a Docker file. Um, I'll share my entire screen. I'll just reshare again. Just a second. I hope you are seeing my screen, VS Code. Let me just zoom it a bit. Yeah. So we are back in our example that we saw yesterday. So this is a Docker application. So I just kept this as a demo. So we have a Docker file in that. A Docker file is a what do you call it? It's a text file basically. It contains a set of instructions that are used to automate the creation of Docker image. We'll look at Docker image right after this. So what Docker file is, it essentially is a set of instructions. It tells the Docker, there will be a Docker software running in your system. It tells the Docker, okay, what to do in order to create an image. Okay, from Python or from Ubuntu, you can have an OS or any base platform on which you are running your application. So from Python, in this Docker file, you are saying, okay, I'm running a Python application, so I need Python. So from Python, work directory is basically it's a CD command in Docker language. So the first words are there, right, in the Docker file in every line that are highlighted in pink. So they are called Docker instructions. So from work directory, copy, run, expose, entry point, CMD, and there are several other instructions also you can see in the Docker documentation. So these instructions should be followed by the parameters that work with that instructions. So you want to go into the app folder, and work directory does that for you. So after going into the app directory, so you are basically cd/app, and then you are copying the current contents into that app folder. So this Docker file is in this location, right? So let me do ls here. So Docker file is in this location, right? When this copy instruction runs, you are basically copying the entire contents in that location into /app folder. When you say /app folder, it's in the container. This is this dot is in your local system, and this folder /app is in the container. So this copy instruction, it's copying the contents from your local system into your container in this path. I hope that makes sense for you. So, and run will run the shell commands, something like that. So pip install Flask. We are basically installing a Flask using run command. And since the application, it is running on this local host, it's not local 000, and the port it's using is 8080. So what this means is the application basically needs a 8080 access to 8080 port, and this port needs to be open for this application to run. So in the Docker file, since the application has dependency on that port, you are exposing that port. Okay. And this is the entry point and CMD. These are basically used to run the commands. Okay. You can have something like um, this will also work, right? It's a Python app.py. It's a simple command to run your application. So entry point basically tells the Docker when when a container is pinned up from this Docker file or image, um, then the first entry point should be this one. So this is basically the starting point of the container. So when a container is pinned up, what should it do? It needs some task to complete, right? So the starting point is this one. That's how you mention the starting point with entry point. Um, okay, so that is a Docker file. So it's basically a text file containing a set of instructions used to automate the creation of Docker image. It essentially acts as a script uh, that tells Docker how to build a containerized environment, including things like setting up operating system in the from instruction, installing dependencies with the run instruction, and copying applications files with the copy instruction. Okay. So you are not someone might ask, right? So you are not mentioning any operating system here. How will Docker know where should it run in Windows, should it run in Ubuntu, where should it run? So if you go for Python, okay, all the images are stored in Docker Hub or any artifact repository. For GCP there is GCR, and for AWS there might be some other artifact registry. So images can be stored in artifact registries basically. Okay, so let's search for Python. So these are Python Docker official images. So if you go there and what was the version which we are using? 3.8, right? So let's search for 3.8. Okay, let's take 3.9. It's not a big issue. 3.9. Let's take a bigger one. Bullseye. Okay, so when you go and look at even these official images, uh, all the Docker file is basically stored in the Git repo, like GitHub repo. Okay, and you can see the instructions again. Okay, these are all the instructions they used to build this Python 3.9 Alpine version image. Okay, there. So what they are doing is they are taking from Alpine. Alpine is basically very minimal operating system. It doesn't have it's basically like 5 MB OS. Okay, the size of that OS is 5 MB. It's very slim, and it's created for containers, especially see, if you say from Ubuntu, then Ubuntu, what will it have? It will have camera drivers, audio drivers, USB drivers, all these extra software, right? All these software, they are occupying the space. They are creating we don't use USB driver in container, right? So we don't need that. So everything unnecessary from the containers is removed or cut off, and a slim image is created. So the point of running containers is for it to be portable, compact. It shouldn't have any unnecessary software. only software which needs to be present is what application needed, right? If your application needs something, only add that. Everything else, remove it. That's the basic philosophy here. So from Alpine, from this version, again, okay, let's go through this first. From Alpine, we are mentioning some env variables. We are setting up some software, again some env variables, and we are mentioning a command for this, like an entry point, right? So this is making use of Alpine. We can go here, and we can again search for Alpine. This is the Alpine image again. You go there, you can see from scratch. This is very important, and you can see the link, right? So using this Alpine image, you are, I mean, using this set of instructions, someone has created an Alpine image, and using, I mean, based on that Alpine image, we are again installing some extra software, and someone created a Python image. What we are doing, we are taking that Python image as base, and we are adding extra software, and we are running our application. So it's like layers, and any base image needs to start with scratch. Scratch is something that Docker provides you to get started. So does did anyone have any confusion or any questions here? It's important to understand the Docker file first before going into further Docker things. So please speak up.
Hello.
Yeah.
Sir, can you explain what is image clearly?
Sure. Okay. So I didn't go to that part yet. So I'll explain it now. Let me complete this Docker file. I'll get back to explaining image now. Yeah, so this example is there from before, right? Where developer has certain operating system versions and configurations here. So what the developer will do now is he will say from Ubuntu, okay, because he's using that Linux operating system. Uh, he's adding the software, he's updating the libraries, and he's adding the software. He's running that instructions now, okay, and he's copying all the files, configurations, whatever application code is there. He's putting that in my path, and he's mentioning a entry point from Python, entry point Python 3.8 to run the application. Okay, so all the instructions will be saved as a Docker file. Okay, and uh, what this is basically is a set of instructions. Just remember that it's a set of instructions that tells Docker what the application needs. It's as simple as that. So we'll look at image now. So we have this Docker file, right? So we will, what we do is we will run a Docker build command, and it will create an image out of it. Uh, so a Docker image can be considered as a read-only immutable template. Like it's a snapshot of that exact uh, Docker file. So it can be thought of as blueprint. So image is a set of layers basically. When Docker, okay, let me go here. So this is an image, right? So image is basically a blueprint. It will tell Docker what to do when a container is pinned up from it. So the flow goes like this. You have a Docker file, you create an image out of it, and you can use that image to spin up multiple Docker containers. Okay, so when a container is being spinned up from a image, these instructions will tell the Docker what to install, what to run. So does it make sense now? I'll go further into this. So image is actually a set of layers and each layer is just the difference of content from the previous layer. So when you are writing instructions, you're copying files from your local system into the container's path. What it does is it will create a layer, and this layer will have the application code. What you are copying, it's all stored in this layer. So every instruction creates a layer. Okay, when you are using here in our example Python, right? So Python is again a set of layers because it's also an image. So layer 1 is Python, which is also a set of layers, and you are stacking more layers on top of that. So let's say in this example the image name is my app, and you are taking this image name and you are writing another Docker file here from my app. Okay, and what happens here is this my app becomes a layer 1. Okay, in this layer 1 all these layers are there. You are just stacking multiple layers on already a pile of layers. That's what happens internally. So all these layers are there, right? Okay, I just mentioned it here. So from app is all the layers again. You are adding 2 instructions that creates layer 5 and layer 6. I hope this made some sense, or do you want me to reiterate again? Okay, I'll just reiterate again, just to be clear on this. So Docker file, it's used to create Docker images. Docker images are used to run Docker containers. 3 things: Docker file, image, and container. Okay, so Docker file is a set of instructions, okay, which you write. Basically you are writing the dependencies and what software your application needs to run properly. Okay, this is a set of instructions. You are just writing the instructions so that in a way that Docker can understand. From this Docker file you create an image. So the image, it can be said as a set of layers. Okay, when Docker file goes through each instruction, it will see, okay, I need to install this Python 3.8. Okay, let me create a layer for this, and I'll store all the Python 3.8 software here. So it will create layers based on your instructions. Okay, the another thing to keep in mind is only few instructions create layers. See, for this entry point, I didn't create any layer. Entry point is just an instruction that will tell Docker what to run. It doesn't need any storage. Okay, so entry point doesn't create any layer. From, run, copy, add, and several other instructions are there. Only those create layers. Now again, back to the topic. So when it goes through each instruction, it decides whether it needs a layer or not, and it will create a layer and store that data or whatever it needs. So once that image is created, you can use that image to either spin up Docker containers, or you can use that image as a base for other images. Okay, so you can use this to spin up containers, or my app is used here again in another Docker file to create another customized image, right? From my app, this is basically a stack pile of layers that were built before, and you're adding 2 more some other instructions, and those 2 will be created on top of this. So I hope this made sense now after iteration. If yes, we can just go to the next topic, like containers. What are
Sir,
containers? Yes.
sir, you mean that the implementation of these instructions is stated as being image?
Yes, it's a snapshot. Like,
Yeah, the implementation of the instructions.
yeah, it cannot be exactly called as implementation, because implementation is like you are running it, right? Implementation means you are running it.
Okay,
Uh,
it's actually it's actually thinking like okay,
it's
this
a
is
blueprint.
the things we yeah.
Yeah, it's a blueprint. So when you actually want to implement all these instructions, how to do it is what this image is. So
Okay.
seeing this blueprint, Docker will implement it in the form of container. It will, when Docker looks at this image, it will create a virtual space. Let's say that might be a Ubuntu. Let's say if we said Ubuntu here only, right? So it will create a virtual Linux Ubuntu, and it will start running apt update all these commands. Okay, based on the image. So why we need an image? We can Docker can just look at instructions and create containers. You can ask, but let's look at this copy instruction. You are copying the contents from your local system when creating an image into the some path. That's just a, you are writing some words here, but you are not actually copying anything. So this is actually done in the image phase. So your actual code or whatever you're copying is stored in this layer. That's why this layer is used to create this image is used to create containers and not the Docker file. uh, did I make sense?
Yes, sir.
Yeah. You can see any of you can ask me n number of questions. I'll explain it thoroughly as long as you understand it. Okay. So uh, this is really important, and you need to understand it to actually work with Docker. Okay, feel free to ask the questions. There is no limit. You need to understand it. That's the goal of this session. Okay, so container. A container is an isolated space. uh, it's a isolated space that has its own processes. In Linux, you have a list of processes. Let me just open a terminal. So this is a Linux system. So if you see ps-ef, you have a list of processes, right? All these are processes. If this terminal is running, it is also running as a process. That's like basics of Linux. So if you run a container in this Linux system, that containers that container will have its own processes again, and those processes are not they don't know that they are running in this Ubuntu system, and there are some other this browser is also a process, right? If I run a container in my Ubuntu system right now, any process running in that container doesn't know that there is a bigger world out there. Okay, there is a Ubuntu system and there is a browser running in that. It doesn't know all that. That's why it's an isolated space. So it's like a frog in a well. It doesn't know what's happening outside. And there is its own processes are there, its own network is there. It will have They will have their own IP addresses. Everything is, it's a small world again inside a bigger world. It's something like that, right? So here we can see the flow again. We have a Docker file. Okay, we build an image out of it, and we can run multiple containers from that image. So each container's life cycle has different states. uh, it can States in the sense, it can be in one of these states in its life cycle from the start of from the point of its creation to its destruction. It Container can be in any of the mentioned states. One is created. It's right after you run a Docker run command from an image. A container is created and it's in created state. So created is just a state to indicate that its container is there. But when an application is actually running, then it will be moved to running state. So in a created state, the container is initialized and ready to run, but it's not started yet. The state is achieved when a container is created using Docker create command. Okay, so the container, when it moves into like okay, so when the container is actively executing an application, or an application is actively running in a container, it is said to be in a running state. When you can spin up a container from an image using two commands. One is Docker run and another is Docker create. If you execute Docker create, the container is just created and no application is running. It's just created. And if you run Docker run, it will do creation and then it will start the application also. Okay. So if an application is in created state and you want to move it to running state, you need to execute docker stat. Or if you, let's say you have created a container out of an image using docker run, it's in running state. If you execute docker stop, that container will move into created state or a stopped state. It will not move to created, it will move to stopped state. So there is a paused state, stopped state. Paused state is the containers process are temporarily suspended, but the container still exists in this state. You can resume the container using docker unpause. Okay, it's a command again. Docker stop state again, these containers processes have been stopped either gracefully via docker stop or docker kill. When a container is in exited state, it's basically entire thing is stopped. If you do docker rm and the container name, it will be deleted completely. I'll show you all these states in the demo. This is just for the PPT sake, I'm just putting this here. So, okay. So before, what was the next slide again? Okay. So before moving into further Docker concepts, let's take a break. So this point I forgot to mention. So every container is pinned up, and a container expects it to run some task. Docker expects container to run some task. Okay, if there is no task, it will not waste resources and it will stop the container. Okay, if there is no task pending inside the container, then that container will be moved to exit state. Just remember that. I'll show what it means in the demo. We'll take a break for 5 minutes and we can get back again.
Oh.
Okay. So the recording has stopped. So, ma'am, do you want to start it again?
Yes, sir, you can continue.
Okay. This is done. So there are two things in Docker. Uh, not only in Docker, basically in containerization. So container runtime and container engine. So we are discussing this as part of the terminology right here. Let me just go, where was that? Yeah, container runtime and container. We have seen what Docker file is, image is, container is. I'll show the demo. Let's complete these two terminologies as well. We'll take a look at Docker architecture, and then we'll execute all the commands, and you'll understand what's happening. So yeah, container runtime. So a container runtime is a low-level software component that focuses on the execution and management of individual containers. So should a container be exited? Is a container you know being created? All the container related things, the actual hard work is done by container runtime. It will manage the entire container lifecycle, including image distribution, container orchestration, runtime management, whatever it is. So a container engine utilizes container runtime. It's a high level component. Uh, it's like, okay, when you take a car as an example, uh, container engine is the uh, things you access. It deals with the user, the steering wheel, the accelerator, or whatever it is. All are high level components, and you are interacting with them to drive the car, right? So they are high level components, while the container engine is an actual engine that does the workload. It will spin the wheels for you to for your car to run. Okay, so that is one analogy. Okay, and container runtime, there are multiple container runtimes which can be used: run C, container D, cryo, etc. Docker was using container D, if I think, and but now it's using container this runtime, run C container runtime. So container engine, again, these are basically the tools: podman, docker engine, cryo, etc. Cryo has both runtime and engine, that's why it's mentioned in both places. So now let's look at Docker architecture. Once this is done, I think the next one is it's next is the demo itself, I guess. Yeah. Yeah. So Docker architecture, what happens is there are three things. One is Docker client, Docker host, and registry. Okay, registry is nothing but Docker Hub, which I showed you in previous session, and today also, where we search some images, right? Python and Alpine. That is registry basically. Registry is not only Docker Hub. There are several artifact registries, as I said. So GCP has GCR, AWS has something else. There are private registries also like JFrog. They can all store images for us. Okay, so just think of registry as a place in cloud or on your own personal server. You can run registries. You can store all the images or application artifacts, jar files, all these things in these places. That's why it's called artifact registry. Okay, now what is Docker client and what is Docker host? So Docker client is something where it can be a terminal or a software that will allow you to issue commands like Docker commands. Okay, it can be terminal or Docker desktop. So if you are using Linux, you can directly install Docker in your system, and you can issue commands using terminal. But on Windows, Docker desktop needs to be installed. Docker desktop again creates a thin virtual hypervisor layer so that you can run Linux containers on a Windows system. Okay, so Docker host is the actual Docker brain, right? So you can have, when you run Docker in your system, both Docker client and host are running in the same system. It's optional. You can have Docker client in one system and Docker host can be in a central server somewhere, and these can communicate over internet, and you can run these components separately if you want. But when we install in our local system, these both run in a single system. Okay, so Docker host, it has a Docker daemon and it's using the container runtime. Okay, and in registry we store public or private images. So all the images like Python, Alpine, which we can use, are public images. But companies, enterprise applications, they want their images to be private. Nobody should be accessing them, right? Or else their entire code will be public, right? So that's why public and private types are there in any public registry. So when you create a container or create images, everything is stored in Docker host. Uh, in this diagram, I'm just explaining the basics. So that's why it's just container and images. There are space for storage, volumes, everything that Docker container needs to run will be handled in Docker host only. Okay, let's understand how the flow works now. Okay, when you run Docker build command from Docker desktop or terminal, okay, it will make use of Docker file. So the command goes like docker build -t image name and the Docker file. Okay, so what it does, Docker build does create an image from Docker file. So the command is sent to Docker daemon. Docker daemon will issue the build command and it will run the build command and it will create an image. That image is stored in your Docker host. Okay, when you run Docker run command, then that image is used and it's used to create a container. Okay, all the interaction that we are doing uh, is through Docker daemon only. So if Docker daemon is down, no matter what commands you run, it will just throw error saying that it cannot reach Docker daemon. Okay, and once the containers are created and you're fine with the container, okay, my image works properly, then you can push the images to registry. I'll show that as well. So this is Docker pull. If you want to use, uh, earlier we search for Python and Alpine images, right? If you want to make use of those images, you can pull those images into your local system as well. Okay, so that's done using Docker pull. When you do Docker pull, those images from the registry are pulled into your local Docker host. Okay, and when you execute Docker push, you are pushing your image into the registry. Okay, so it works like that. So you can have multiple containers, obviously. So any questions in the Docker architecture so far? Okay, I'll show the demo and then let's see if we have any questions. So these are all the Docker commands and we'll be using these right now in our demo. Okay, so let's go to our Docker file and we are in, I hope you are able to see the letters in my terminal. If not, I can zoom it a bit more. Guys, speak up. Okay, so this is the CI demo folder and in this folder there is a Docker file. Okay, so now this Docker file, as I explained before, it's running this Flask, this app.py, which is basically a Flask application. Okay, and we need to build an image out of it. So you remember the flow, right? From a Docker file you build an image and from that image you spin up containers. So the command to create image out of a Docker file is docker build. So docker build -t. -t is used to tag the image. It's basically an alternative of naming the image. So when you tag an image, you are basically giving that image a name. uh, let's say it's a Flask image. image and dot. Why you are mentioning dot? Because our Docker file is in the current folder only. If it was there in some other location, you give the path here. Okay, when you do this, it will start building your application. So it will what it does is it will look at each instruction, okay, and it will create layers in the diagram we saw earlier, right? Every instruction will create a layer, and it will make use of caching technology as well. I created this image before to test and see if it works or not. So the layers were already present in my system. That's why it made use of the cached layers and it reused them. So that's why the image building was faster. When I first built this image, it took some a minute or so. Okay, so now if I execute Docker, okay, let me clear this. Okay, now to see if the image is created or not, you can type Docker images, and okay, there are a lot of images in my system, and this is the image which we built just now. Oh, it's a 16 hours ago, but we gave the Flask image only. I think it's because it reused the layers from before. It did this. Let me just RMI Flask image. Okay, it untagged the name and it deleted the Flask image. So when you execute Docker images again, you can see that image is gone. Let's execute the Docker build command again. See, it's making use of the cached layers and Docker images. Okay, the Flask image. It made use of the previous layers. That's why it's you know created data 16 hours ago. So now that our image is ready, we want to run a container from that image. So the command is docker run name Flask container, and we are exposing a port, right? So I need to maybe so let me just open this. So this is my system, let's say, and we are running a container inside it. So there is a port, and this port is 8080. Okay, so for us, we are in this system. We are not inside container, and our application is running inside container. So how do we access this application that's running on port 8080? What we'll do is there is port 8080 on our system also. What we'll do is we will map this port to this one. It's bidirectional. So we need to tell the container that you need to map the port on my system to your port. How we'll do that? It's done using -p 8080. It's so the first one is my system's port and the second one is my container port. And I give the name, I give the port, and it will be the image which needs to be used for this Flask image. Yeah. So what it does, it's running in the forefront because I didn't specify any options. Okay, if I open, so you can see the hello world printed here. If you can see it, this is the hello world. Why it's printing hello world? Because we mentioned it to print here hello world. So you are running the application in a container, and since you mapped that port, I can access the port here. So what is this 17.17.0? I mean 172.17.0.2? it's not my system's IP address. So if you do localhost address and 8088 also, you can see that hello world. Okay, so, but I'm not having access to my terminal. So if I do this, if I check my container status, docker ps, I don't see any container. What happened to my Flask container? So docker ps -a, you will see that Flask. This is the Flask container. Okay, and it's using the Flask image, and it's in exited state 15 seconds ago. Okay, so let me just remove that rm Flask container. Okay, now if you do docker ps -a, you can't find that. Now let's spin up another container. Now this time I won't give any name, and I'll say -d. Okay, so now it didn't give me any URL. So how do I access it? Do I know if it's running or not? I'll execute docker ps again. So it's running, even though the task is not there, it's still running because I gave a -d option. Okay, and since I didn't give any name, it will come up with some weird interesting names, strange McLean. And if you see my previous containers, it will have some other names like Sharp, Goldberg, some weird names, just to make the container unique. So this is our container, and port is mapped to 8080. Okay, let's see if it's working, and it's working, right? And your container is still up. So if you want to stop that container, your command is docker stop, and you can either take the container ID, or you can take that name and execute commands. Let's just take the container ID this time. Okay, Control Shift C, Control Shift V. Okay, docker stop. It will take some time to stop it. It stopped it. When you get the same hash again or name again, that means the command is success. Okay, docker ps -a. Now you can see the container is just stopped, and it's in the exited status. You can start it again using docker start strange underscore McLean. Okay, if you get this same name again, that means it's a success. And docker ps, you can see it's in uh, up state. That means running state. And if you re-execute again, refresh again, it's working. So if you want to remove the container, then you can stop it, and then you can do rm docker rm. rm and okay, so if you do docker ps -a, there will be, you might have seen other commands like docker container ls. Okay, that will also work, but these were previous commands, so I'm familiar with them, that's why I'm executing them. These are the newer version commands. Okay, both work, so it's up to you which one you want to use. So we have removed the container, and it's not showing up anywhere. So docker images is command to list all the images in your system. Okay, Flask image is there. If you want to remove the image, rmi is the command, and you need to give the image name, and it's gone. Okay, when I say it's gone, only the layer is gone. That's why if I build a new image again, if I want to build the image again, it will make use of cache layers. That means the previous layers which were there, they still exist in my system. They are still taking up space. Okay, when only the layer which is tagged, it's deleted. So docker push is the command to, let me just show that. Where was the build? Yeah, right. So build command, see it is still making use of the cache layers. That means these layers are still present in my system. So I'll run the docker run name my flask, okay, and -p 8080 dot, and it will, oh, what happened? Oh, docker run -d, let me give that, and it shouldn't be dot, it should be the image name, flask image. Dot is used for build, I just got confused there. So the hash id is printed, and actual hash id is this one, but if you do docker ps, you can see a smaller version of that hash id, okay, the only first few characters, okay. And if you want to go inside the container, running container, then you need to execute this command, docker exec -it means interactive, and what was the container name, my flask, and then sh, you are inside the container now. Let's type host name, does it work? Yeah. So this is basically the id of the container, and that will be the basically host name of that container. So you can go inside container, see what files are there. See, we did a copy instruction, right, from in the third line, like copy whatever in this folder into the app folder. The location you are is this app which we created, and we copied all these files inside the container, right? So you will find all these files here. Did it make sense now? Like you are instructing the uh, docker to do these, okay, while writing this, okay. Docker will read these instructions and then create an image will have all the files, and since you are spinning up multiple containers from a single image, all of them will have the same data. Any questions so far? So no questions in the sense, I hope you understood all these. So few things I want to mention is docker inspect. We'll look at this again. So docker inspect my flask. So what it does is it will give you every detail about the container, okay. So it's a lot of data. Let me see if I can copy all this into the code editor here. Yeah, this is better. So you have an id, this is the hash, okay, created date, what is the path, like this is the entry point which we mentioned here, that's Python, okay. These are the args, that is the cmd, okay. And what is the state of the container right now, okay, when its status is running, was it passed, was it restarting, the process id of that container. If you grab ps-ef, then you will have the container. One among these is, okay, let me do a grep then. Fun grep 9944. You see it's Python app.py. Okay, you are getting the command 9944. That's what this is. This command is something we mentioned here, Python app.py, right? So this is the timestamp, what image it's using, okay, path details, name, what is a driver. I'll come to this overlay too, okay. And there will be something important here, volumes, remember that. See, you when you play around this with these containers, you need to see all these details as well. At least you don't have to remember exactly, oh, there will be a graph driver, there will be data, there will be 4 things inside that. Don't do that. Just take a look at those and remember that, okay, something like this exists in the Docker config or inspect. Okay. Where is the IP? Yeah, network settings, right? Inside network settings, you will have IP address as well. So this is the IP address of the container. So remember, when we didn't give -d option, it printed two URLs which you can access. One is the localhost URL and the other one was 172.17.02 slash sorry colon 8080. So that's the container's IP address. Okay, and there is a gateway address as well that was created. So when you install Docker and when you start running containers, a separate network is created for the by default for these containers to communicate. Okay, there will be a MAC address for the container as well. So the 172.17.02 is the IP address of the container. Let me see if I can spin up one another. I have several images, right? Docker images. Okay. There is yeah, we have a busybox image. Busybox is just a Linux system where you can log in and execute some commands. Docker run -d hyphen name busy busybox. Okay, there is another created that's created Docker inspect. Let's do this. Busy. Now we will have another IP address, probably .3. I'm assuming. Oh wait. So this is only, I didn't give any port numbers to this. -p. Oh, I need to delete the first one. Stop busy. Docker rm. Name. Okay, I need to give it in front. The order of giving the parameters also matters. Busy2 is already running, so Docker rm busy2. Okay, it's created now. Docker inspect busy2, and there is no IP address created for it. Why? Because we are not running any application inside it. Let me go into the Docker exec -it busy2 sh. It's not running. That's why Docker ps -a. As long as it's running, it should be having an IP address. So since it's exiting, it has no task. So whenever this is created, since there is no task, Docker is moving it to a exited state. So we will have to give it some task. Let me put ITD. See if it's running now. Okay, it's running now because I gave it the IT option, interactive option. Docker kept it alive. So let's inspect this now. Inspect busy2. So now you have the IP address, and it's a 172.17.03. If you want separate network to be created for your own containers, then there are Docker network commands as well. Docker network. If you do tab, then see you can have options: connect, create, disconnect, inspect, ls, prune, rm, all these things. So you can create your own network using a range of IP addresses, and you can spin up containers into that network by specifying -- network option in Docker run. Okay, so these are Docker basic commands. Any questions so far? Okay, so I'll go back to PPT then. Okay, one another thing I wanted to mention is how you are mapping a port to your container port. Let's say there is a folder here called something like my folder. Okay, you can map this folder to the container, and inside that container there should be some other folder, like again my folder maybe. You can have the same name, no issues. So these are called the process, or the terminology used for these is called volumes. Okay, so this is called port mapping, this is called volume mapping. Instead of copying the entire uh, entire files into the container image or Docker image, you can have a folder separately for it. Why is this used? Okay, so if there are only like 10 MB files, 20 MB files, you might want to copy them. Okay, that's fine. But let's say there are some files like 10 GB. Okay, if you create an image out of it, the image will definitely be greater than 10 GB. But the point of microservices is to have less image sizes, right? To promote faster deployment and all. So if in that cases you want to separate that 10 GB files, place it in a different folder, and you can map that to the container, not the image, the running container. That way, okay, let me just oh shit. Okay, that way when you have multiple containers running, you can use the same folder and map it to all these containers. This can be shared among all the running containers. Okay, this is called volume mapping. The volume mapping is done using Docker run, like -p 8080 or 8080 is used for port mapping, right? Similarly, -v and source folder like on your host and destination folder on your container. It can be used like that. Hope that is also clear. So the best practices, obviously, in Docker file, while writing a Docker file, it's always best to have multi-stage builds wherever it's applicable or suitable. I'll tell you what multi-stage builds in a while. Okay, 1 second. So fine. You can use multiple from instructions in your Docker file to reduce the final image size by copying only necessary artifacts. I'll explain what multi-stage builds is. It might be a bit confusing, but I'll mention that. So choosing the right base image, as I said, you can choose from Ubuntu, but that will have all the unnecessary software your application might not need, right? So you can choose Alpine or whatever is more suitable for you, and you're not wasting any space for uh, unnecessary software. Okay, so minimize the image layers. You have, as I said in the previous slides, where image is all about layers and Docker file instructions create layers. If you give, let's say if I give here another layer called run some apt get uh, apt get update. Now what will this do? This run fourth line, this will create one layer, and this will create another layer. So the number of layers increased by 1. Instead of that, you can just do and apt get update here itself instead of this run instruction. So you have reduced the total size by 1 layer now by just doing this. So this might be minimal in smaller applications like this, just starting applications. But when you have larger applications, it significantly reduces the image size or image layers. So specific image tags. So now I have built a image out of this, right? So it will have the Flask image colon latest. It will be like Flask image latest. So when you make some changes and build the next version of the image, it will just override this one if you don't specify any tags. So it's always advised to use the versions or something like that to identify or to have a different version of your image, so that it's easy to revert back to previous images in case of any code issues or any bugs that went in. Okay, don't give root permissions to your applications inside running inside the container. Okay, that's one thing. And optimize caching. We saw that just now, right? It's faster to build images when caching is enabled. It will not build the layer, it will just reuse the already existing layers. So the next one is yeah, these are best practices for Dockerfile, and there are best practices for containers as well. So you shouldn't expose unnecessary ports. You should expose only what your application needs. Don't give any privileges like extra permissions to processes in your container. Uh, any unnecessary capabilities need to be dropped, like admin permissions or admin capabilities need to be dropped. So similarly, there are read-only file systems. Unless you want your application will write something and change the data, just give read-only file system. Read permissions should be given, not execute and write. Okay, in Linux, RWX will be there, right? It's about that. So limit resource usage. So all these containers, where was that diagram? Containers, they run multiple. We can run multiple containers in a single server, right? So if this container has some faulty code and so that runs in some infinite loop, it will keep on continuing, it will just keep running and it will consume all the CPU and memory resources, right? And the server has some like 10 GB 8 GB RAM and 10 GB memory. All that will be used by this one only. So what will this container have? So this will also get impacted. So one service is now impacting the other service. This is not how microservices need to be run, right? When they are split, because they need to be independent of each other, and one service's fault shouldn't bring the other service down. So that's why you have to set limits on each container, so that even if the faulty code is there, it's not impacting the other thing. So we will look at that more in detail in Kubernetes, container orchestration. Okay, limit resource usage. Rootless mode, this is the same as this one. So any sensitive data should not be added into the like open passwords in terms of plain text and all. Regularly update images and dependencies. So that's best practices. Now we'll look at multi-stage Docker file. So when writing a Docker file, let's say this is the one, we are naming this particular from instruction as stage 1. Okay, when you do this, all the following instructions come under stage 1 only. This is like aliasing, right? So what this is doing, this is installing Java 11 Maven. It's copying the code into my path. It's running some Maven command to build a jar file. So out of these, when you run this, you will get an output that is a jar file, .jar, like my application .jar. It will be only like 10 MB file, let's say. Okay, but Java is also again 15 MB, let's say. Maven is again 5 MB. So the image as a whole will be like Ubuntu, let's say 300 MB, and these all again 350 MB, let's say, right? So the total image size will be 350 MB, and you are just building a jar. You are not even running the application. So in multi-stage Docker file, you can add in the same file, you can add another from instruction, and you can copy the jar file that was built in the previous stage. You can copy that from the previous stage into this stage. So from the first from to the next from, this is one stage, and this is the next stage. Okay. um, you are just copying whatever is needed from the previous stage, and you are executing that jar file. So when you build an image out of this Docker file, you will not have Ubuntu, Java 11, Maven. Okay, you will only have Alpine, the jar file which was built before, and the whatever is there in this stage. So you are reducing the size of the image from 400 jar file 10 MB, 15 MB, and maybe you need Java also. So you are just having maybe 50 MB image instead of a 400 MB image, and it really makes a difference when you use it properly. So yeah, this is some comments again to understand the image. It could be of 800 MB, including Java, Maven, and some other dependencies, along with the code and jar file that is 25 MB. Okay, you copied that jar file which was 25 MB from stage 1, saved storage space by removing all these Maven and other things which are just needed for building the jar file and not needed while running the application. Okay, so that's why when the image is built out of this multi-stage Docker file, all these are executed. A jar file is created, and that jar file is used into the next stage, and all these are discarded later. Okay, that will be image size of 150 MB instead of 800 MB. I hope this is clear. Any questions in this multi-stage Docker file? Okay, so volume and port mapping, as I said before, you can map a folder using -v option, and you can map a port also using -p option. We have already seen this in the demo. Okay, these are the commands. Okay, so the Docker volume create command will create a Docker volume folder inside the host system. Okay, and you can map that volume using this -v command. You don't. Okay, you can ask a question. Okay, sir, do we need to create a folder? I mean, Docker volume create to have the folder. Only those can be mapped to the containers folders. No, it's when you do Docker volume create, it's easy to manage. When you do Docker volume ls, you can have list of volumes that containers are using. So it's easy to manage. You can create any Linux folder, any random folder, and map that to the container. Okay, so yeah, this is about volume mapping and port mapping and Docker networks. So Docker has several types of networks. By default, uh, it's a bridge network. Okay, let me just go back here. Docker, yes, oh, both are running good. Docker inspect bz2. Okay, it's using network as bridge. Because I didn't mention any specified any other network specifically, so that's why it went with the default network protocol, that is bridge. There is a network called host. What it does is it will map the containers network to the host network. This option is rarely used. If you want to practice, bridge is enough. So none is used when a container orchestration tool like Kubernetes is used to run Docker containers. Kubernetes uses some other network protocol, and Docker, if it's using bridge, there will be a conflict in network communications. That's why none. When you set Docker network as none, Kubernetes network protocol will take priority, and all the communication happens using that protocol instead of Docker's protocol. So similarly, there are overlay and IP VLAN. So IP VLAN networks provide full control over both IP and IPv6 addressing. If you want like to the lower level customization, you need to select that IP VLAN and MAC VLAN. Overlay networks connect multiple Docker daemons together. So you have multiple Docker hosts, not just a single one. There are multiple Docker daemons running. Then you need to select overlay so that you can connect all of them together. Okay, this is like running multiple clusters kind of thing. Let me just Docker. Yeah. So this is basically docker.service or Docker daemon. It's running, and when we execute any commands, this will be they will be going to Docker service, and Docker service will take care of it. As I said in that architecture diagram, this is a Docker daemon which is running. So if it goes down, whatever commands you execute, they don't work. So that is about networks. Yeah, let me start the slideshow again. So Docker Compose, there is this thing called Docker Compose. Why it's needed? Let's see about that. Let's say for your application, you need 3 front-end containers. Okay, it's 347. 3 front-end containers, 2 back-end containers, and several containers where your database is being run. You can if you go here, you can search for MySQL. You can have database also running inside a container. You can have MySQL, PostgreSQL, whatever database it is. Images are available for that as well. So front end, three containers, 2 backend containers, 4 database containers. Let's say. Now, if you want to run this setup, okay, you need to execute like 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 commands, 9 Docker commands, right? Only for this small setup, we are executing 9 commands. Every time you need to bring it down or bring it up, whatever changes you made, and you need to redeploy the entire application again. You need to execute all these. You need to have a shell script maybe that loops through each command and executes it. It's a headache, right? So what it does is Docker Compose, when you write one YAML file uh, with all the dependencies mentioned clearly, when you execute one command, Docker Compose up, all the setup is brought up automatically. And when you execute Docker Compose down, all the setup is destroyed automatically. Okay. So Docker Compose is a tool used for running multi-container applications in Docker. I can just show one of the, no, not this, sorry. Is I have a Mimir stack. Okay, I'll just find it. In the meantime, if you have any questions, please go ahead and ask. There is 10 minutes time, and as you know, this is my blog and this is my LinkedIn profile. If you want to connect, you can connect. I'm stopping the presentation just now. I'll find the Docker Compose. If I am able to find it, I'll just show it now itself. In the meantime, if you have any questions, please go ahead and ask.
Hello, sir.
Yeah, ma'am.
Yes, sir.
I'm just looking for any questions if anybody has.
Yes, sir. Yes, sir. Yeah, participants, any questions from your side or any doubts? I've shared my shared the previous recording also to you all, if you check. Similarly, I'll share this recording also. You can try on your own. But other than that, any doubts, please ask now. I'll share the attendance link right now. Wait.
I just found the Docker Compose file. I'll just go through that quickly. So this is one of the Docker Compose files. So it's set up like this. You mention whatever containers you want to run as services. This is one container. This is another container like that. Okay, and you give the commands. When you spin up the container, what command does it need to run? Okay, does it have any dependencies on other containers? Okay, let's say in the previous example, 3 front ends, 2 backends, 4 database pods were there, right? So you want the database containers to come up first. After that, you need a backend containers to come, like in a sequence. If you have such dependencies, then depends on needs to be used. So this particular alert manager service, it needs or alert manager container, it needs min.io and distributed containers to come up first. So that's why it has depends on clause here. These are the environment variables, port mappings, volume mappings, the image it needs to use, and the actual container name. So when you give all the container names, its dependencies, and all the configuration here, when you go to this folder and do Docker Compose up, it will go and look at these dependencies and stuff. It will bring all the things sequentially as you mentioned in the file. So Docker Compose is a tool that helps you, bring up these multi containers and manage them easily. I hope that made sense. So yeah, that's it from my side, ma'am, for today.
Yes, dear participants, I have shared the attendance link. If you check, you can post your attendance now. So if any doubts, please ask sir. So shall we close then, sir? Okay, that's it.
Yes, ma'am.
Yes, is it okay? Okay. So others, if any doubts, please raise your doubts. Okay. So anyhow, I'll share the recording soon. So you can try it from your side, and if any doubts, even tomorrow also you can ask. So I declare this third day session is over, and I request everyone can leave now, and we'll meet tomorrow by the same time. Thank you to our resource person and to all the participants. Thank you.
Thank you.
Thank you.